Hello everyone, good evening, and today here we are here for the Professor N.R. Kamath Distinguished Lecture by Professor Herbert Huppert from the University of Cambridge. Before we get started with the talk, let us look at a short video on Professor N.R. Kamath and relive his legacy once more.
Guru Brahma Guru Vishnu Guru Deva Maheshwara Guru Sakshat Parabrahma Guru Sakshat Parabrahma Tasmai Shri Gurave
The chemical engineering profession and teaching in India has been uniquely blessed by the benevolent touch of an illustrious guru, Professor N.R. Kamath. N.R.K. took up the position of Deputy Director in 1960. As the Deputy Director of the Institute in the early formative years, Professor Kamath held the center stage and undertook the yeoman task of setting the framework and processes to streamline the running of academic programs. He was credited for drafting the Institute's earliest academic offerings and considered the father of all academic things, who strode the Institute corridors with the rules of his tongue. For many students, Professor Kamath was the inspiration that set them on the road to success. For some other students, his shoulders were the ones on which they rested their problems. For many young faculty, he was the ultimate mentor and role model. For the underdogs, he was their champion. For the institution, he was the epitome of an educationalist par excellence. Gurus such as Professor N.R. Kamath help shape great institutions and bless the individuals in it with the priceless and sublime gift of knowledge that sustains over several generations. Thanks, Professor N.R. Kamath, for this priceless gift of knowledge and pioneering mentorship. You will always, forever, live in our hearts.
So, on that note, I would like to welcome Professor Mahesh Tirumkodulu, Head of the Department of Chemical Engineering, to say some words on Professor Kamath and also introduce our speaker, Professor Huppert.
Thank you very much. So, good evening to all of you. I'd like to give a very short intro to Professor N.R. Kamath. Of course, we've seen the video. In fact, in today's distinguished lecture, we celebrate the legacy of a visionary academic leader who transformed engineering education and research in India. The world-class undergraduate program that we now have at the IITs, the standard examination for admission into IITs, and the idea of a modern industry-academia collaboration are all the culmination of the efforts of Professor Kamath's dedication to education and research. When he was here, he not only served as the head of the Department of Chemical Engineering, but he was also the Deputy Director of IIT Bombay. So it's in his memory that this distinguished lectureship has been instituted by our distinguished alumni. So it's both an honor and a pleasure to introduce Professor Herbert Huppert, who is a distinguished figure in the realm of geophysics. Born in Sydney, Australia, Professor Huppert's academic journey began with a first-class honors degree in applied mathematics from Sydney University, where he was awarded the University Medal and the Barker Traveling Fellowship in 1964. He then pursued his PhD at the University of California, San Diego, under the mentorship of John W. Miles, who's a very towering figure in geophysics. In 1968, he joined the University of Cambridge as an ICI postdoctoral fellow and has since become a cornerstone of the institution, holding positions such as the Assistant Director of Research, University Lecturer, and since 1989 as Professor of Theoretical Geophysics. He's also served as the Foundation Director of the Institute of Theoretical Geophysics and has been a Fellow of King's College, Cambridge since 1970. Professor Huppert was elected a Fellow of the Royal Society, FRS, in 1987. In 2005, he was the only non-American recipient of a prize from the United States National Academy of Sciences, being awarded the Arthur L. Day Prize and Lectureship for contributions to the earth sciences. He has been elected a Fellow of the American Geophysical Union, the American Physical Society, and the Academia Europaea. In 1920, he was awarded a Royal Medal and named Scientist of the Year in Earth Science. Professor Huppert's research has significantly advanced our understanding of fluid dynamics in geological contexts, with applications spanning meteorology, oceanography, and geology. Beyond his academic pursuits, Professor Huppert, I know, is a very good tennis player, and has a penchant for engaging storytelling, often weaving humor into his lectures to elucidate complex scientific concepts. And hopefully, we'll get to hear some of that today. So please join me in welcoming Professor Herbert Huppert as we look forward to his talk titled Particle-Driven Flows in Theory, in Environment, and in Laboratory Experiments. Please join me in welcoming Professor Herbert Huppert.
Okay, well, thank you very much, Mahesh. That was a very kind introduction. And we'll play tennis after this? Good. And thank you all for coming. You can come and join in the tennis match. It's been wonderful being here, just as it was the previous times I've been here. Everybody's been very good. And I'm happy to talk to as many people as would like. Just come along and Riddle will tell you where my office is. I don't know, I'm afraid. But I'd like to tell you today something about my recent work on particle-driven flows in the environment and the laboratory. That was a wonderful description of Kamath, both in the video and Mahesh, and I'll try to live up to him. Now, I'd like to start with this example of a particle-driven flow. It's going to fall down because of the snow and ice particles. And I like this because I used to go climbing with my wife in Austria, and we were once quite high up on the snow, and an avalanche like this suddenly came. And my wife said, "Run, run!" And I said, "There's no point, Felicia, because it can outrun us or it'll fail. And if it outruns us, let me tell you, it's over." Well, you can imagine what happened. Well, my wife was amazed and said, "How did you do that, Herbert?" And I said, oh, it was easy. I just thought about the Navier-Stokes equations and I substituted in the size of particles. And at about that stage, she said, shut up and just keep on walking. Now, but this is, I think, a nice example. But since coming to India, I realized that there was a much better example, which is for the first time I was in a Holi celebration and little particles were being thrown around by everybody. They were all supplied. There wasn't much geophysical aspect, but boy, there was a lot of color, better than in ice, that's for sure. Now, I'd like to tell you really about 3 different investigations that I've made, still with a lot to come, and I'll explain some of that. And Mahesh is listening very carefully to that because that's saying, could I please be invited again? Right. Particles often get into the environment. This is a bad shot in the sense that it's industrial waste being just thrown out into the water. I can't speak. I can't speak for India, but I can for Cambridge, where the Cam is being flooded with junk, and people object to that, but the companies that put out their waste don't seem to be so disturbed. And there is the question of how far do the particles go? When they're heavy, will they drop and no longer cause troubles? Another example is ice particles going into the Antarctic Ocean, as happens quite a lot. How far do they go? They're ice particles, and so they're lighter. Now, I've done quite a bit of work in the Antarctic and ice, and I once went on a wonderful oceanographic expedition to Antarctica, and about the 3rd day or so, I said to the captain, look, I'd like to make some measurements close to one of these icebergs because I have a theory of what should happen. It would be nice to make some measurements. And he said, how close would you like to go? 20 yards or something like that, 20 meters? And he said, no, under no circumstance. That would be so dangerous. No, we're not going anywhere near that. The closest I'll go is about 150 meters. I said, well, I won't get many measurements there. Okay. About 3 or 4 days later, there was a knock on my door at 2 in the morning. I thought, what the hell is this all about? And I got up in pajamas, and there was the assistant captain, or the second captain, and he said, coming close to me, I heard the discussion with the captain. He's now asleep, and I know him. He'll be asleep for 4 or 5 hours. I'll take you as close to the ice as you like. Fabulous. I was very grateful, but I couldn't mention it. Here's another example of particles coming down from a rock slide. Whoops, does this work? Yeah, from a rock slide and going over the road and into the neighboring lake. Now, whether anybody was caught there, I don't know. But if not, if there was a car just here, he would also say, shut up, Herbert, and just leave me alone. Here's another natural example, which is really interesting. The eruption of Montserrat in 1995 led to lots of these pyroclastic flows. Why? Now it works, yeah. These pyroclastic flows, which are hot, heavy ash particles. But because they're hot, they're not as dense as the cold ash particle will be, and it flowed out over the neighboring sea. And of course, one wants to know how far they would go. Here's another example of particles being sent out by a big volcanic eruption of Mount St. Helens in 1980, and hot ash particles again. And there was a man somewhere here, and that was the end of him. And there was another man here taking photographs, and apparently he prayed to God that he would be spared. And just, he says, as he finished praying, it lifted up into the air because enough particles had been dropped out that the hot air that had taken the eruption was density less than the cold air here, and it went up. Now, he, of course, has a different explanation, but there it is. I couldn't resist this. This is a typical English summer evening. You guys don't understand this. I've been here for 10 days. It hasn't rained once. In England, you couldn't say, I've been here for 10 minutes and it hasn't rained once. But this is really happening. Snow in central London. Well, it's an environmental particle. How will it go? Okay, well, there are also particles that go to the bottom of the fluid and spread. They're more difficult to take photographs of, and all I could do is show you this sketch. And the question is, how far will they go? And that's partly true with the heavy particles in the industrial waste. Well, to see what's going on, and I'm going to tell you 3 different studies that I've done, I want to tell you of some experiments we carried out. We started with some experiments where we had a long tank like this, a little longer than that, 2-3 meters, and we put some particles that were less dense than the water, though we could add salt to make the... Why can't I always get this to work? To make the density of the liquid larger. And then we'd lift it up, let it go, and watched how this length and this thickness, if you like, varied with time. And we did the experiments first, as I think is the right way to do it, and the theory I'll tell you about in a little later. This is what it looks like. You see the particles here, light particles, so they come up. We didn't fill the whole area or volume behind the lock gate, but we lift it up and out it goes. And one of the things that we found most surprising is there's not much motion at the back here. In fact, this has hardly moved at all. It does move later, and it ends up like this, and as we'll see, it doesn't go forever. It stops, but it still has some thickness here. So these are light particles that are held down by the heavier water. That's not me. He hopes. Here's another experiment, just deeper, just to show how... What was that? Mahesh, are students shooting at me or something like that? You're sure? You wouldn't allow that. It's deeper, but again, you see there's not much movement here. But it does come out in the end, and it's sort of rather straight there at the bottom. So here's a typical example where we see the... I will get this to work. Come on, yeah. We see the distance of the front, which starts a little bit away from the back of the tank, and it goes up and then stops. It goes, it spreads almost uniformly in a log-log scale with a slope of beta. So the position of the front goes like t to the beta, with beta here about 0.6. And then you see it very quickly decides it's had enough and it stops. Oh, and I should have said where I come from in Cambridge, we ask questions during seminars. We interrupt people and we try not to shoot them. Well, could I suggest if you want to ask questions at any time, please do interrupt, put your hand up. So
can you go back to the image, the experimental? So yeah, I was wondering, we see this in terms of energy, in the context of energy. How does the front move? So we have some stored energy because of the buoyancy, and then you lift it up, and there is a free boundary that can move, and that's how the front moves.
yeah, they can.
The buoyancy that driving the front.
Yeah, I mean, there is the buoyancy. All of these particles, even these down here, are less dense than the fluid. So what they'd most like to do is to rise, but the fluid above them says, I'm first. And that's what you see here. I'm first. They're probably not, whoops, sorry. Whoops, eventually I'll get it. Yeah, so they don't move, but then with time, because if you like, the number of particles above them is sufficiently few that they can move up. Okay? And I pat you on the back for asking a question. You can all get patted on the back. You just have to put your hand up and ask a question. Okay, this goes like, this just shows the difference in salt water and fresh water. Not very different. You see that they both go pretty much at the same rate and stop at the same place. That doesn't play much of a role. Here's now looking at a number of different situations, different lock lengths. I hope it's not my eyes. It seems slightly out of focus. Is that right?
Maybe slightly off.
Okay. And you see on the log, they all go with more or less the same rate. Now, here's some more trying to understand what it goes like. We've said that it goes like alpha t to the beta, but what do you decide what beta is? Well, it's a non-dimensional quantity, and so you want to see how it compares with another non-dimensional quantity. Okay, and so now we want to plot it against a non-dimensional number as well. So it's the initial, it's length where it is against the cross-sectional area to the half. And I've used V here because my student used A for something else, which I would have rather had as the area. But this is basically the area to the half. You didn't give an introduction to this disturbance. He's talking as much as I. Now, here again, it's looking at the A here, and you see that the A here, non-dimensionalized, and this is what I said, can be fitted to a really good curve, even for all the different experiments. Now, because it all, fits to a large amount here, we've plotted all the positions of the front as a function of time, non-dimensionalized in this way. And you see, not at the beginning and not at the end, they all slow down differently, but in the middle, they're pretty much at 1, where this green line is 1. So that means that we can collapse all the experiments. But now, if we look at the final position as a function of the initial position, we really find that the graph's all over the place. But again, we non-dimensionalize appropriately, and take the non-dimensional final position, and we see that can all go together, which is really very good. Now, this is some observations of the beads layer, and this now plots the thickness as a function of time, and it goes down, as you'd expect, but then it also reaches a constant. A few light particles here just can't go on any further. And here we want to non-dimensionalize it and see that we can do it. And what we find is that under certain circumstances, the bottom doesn't move at all. They're held back, but we can reasonably fit the data. Right, okay. So now here, gee, I can't hear it now. Now, here we have the distance of the front as a function. Gee, this is so out of focus. As a function of time, and these with the heavy ones, I think, and these are with the sorry. One of these is for heavy ones, one is for light ones. Buoyant ones, B is this is the buoyant ones, and these are the heavy ones, because we can put heavy particles in there. And here are the shots that you see for the light ones. And what is interesting is when you look in detail and carefully, at first the front doesn't move very quickly as a function of non-dimensional time, and then it begins to move rapidly and then goes down. All the different experiments go down almost on the same line. And this is just seeing it again for different values. Well, this just says what happens if you scale the particle front velocities to have different initial conditions. They all go at the same slope in this non-dimensional form, but they're put off a bit because it depends how much you have. But this is the non-dimensional relationship we find, that if we non-dimensionalize the velocity of the front in this way and the time in this way, that's really quite obvious, then it looks like this for the non-dimensional time between 15 and 40, and then it looks rather different. Now, it's not a discontinuous change, of course. Mahesh is gone. Maybe you should all go back there and come. It's not that bad a talk, is it? Well, we'll see. So now, and he wanted an equation. Here's the equation that talks about what we can do theoretically. The first term is the inertia, d is the particle diameter, this is the velocity of the particle, the density of the particle, this is the buoyancy that's letting it go up, and this is the viscous drag on the particles. This is the coefficient of viscosity. And now if you non-dimensionalize that appropriate, you find that you get something that looks like this, and you can solve that as well. Here is some more data. I don't think I need to show you the data. This is now just a picture of what it will, I hope, look like. This is what happened in the Tonga eruption in 2021, when there was a volcanic eruption below the sea surface at bottom, and it came up to the surface and then made a cloud, an eruption cloud that went into the surface and carried quite a lot of particles with it. This is for some observations. And then the particles dropped out and you just had the hot air that spread. And that's really an important problem, where it goes and how it goes. And one thing that I always find fascinating, and you may not know, well, you won't know the second part. The first part you will know. Oh, can you hear me at the back? You don't say anything, so I assume it's no. Can you hear? Not that well. Okay, I'll talk a bit louder. You may know that there was an eruption of an Icelandic volcano called something that begins with an E, and I can never remember how to pronounce it, so I just call it E. And E erupted, and all airlines were stopped. It wasn't possible to take a flight for about 2 weeks because it was thought that would be very dangerous. Well, the first thing I'll tell you, which I bet none of you know, but is fascinating, the reason that all the flights were stopped was because the engines in all airlines are not owned by the airlines, but they're owned by the manufacturers. So Boeing and Qantas and Air India don't own the engines. They're owned by Boeing or whoever has made them. And the engine manufacturers said, we're really nervous that this could cause difficulty, and we're not going to rent the engines to you. It's in the contract that we can stop the rental whenever we like. Now, of course, some airline companies went bust because of that, but the airline manufacturers or engine manufacturers didn't lose much money, though nothing happened. In actual fact, I had a graduate student do some calculations, maybe I should have shown them, where the volcanic plume was taken by the wind on a very, very small scale. It never went anywhere near any of the airline routes. It could have, it was ridiculous. It wasn't needed at all. Some airlines went bust and they didn't like that, but the engine manufacturers said, well, we just lost 2 weeks rental. That doesn't matter. Now what I want to do is to tell you some calculations that we've done using the Lattice-Boltzmann method with, now this is done by some Chinese colleagues of mine, 28 million LBM cells, and it needs 800 minutes of calculation to just go forward for 10 seconds. So occasionally I send an email and say, look, would you like to do this and this calculation, please? And they say politely, go to hell, Herbert. That will take us at least 3-4 weeks. We don't need to do that extra calculation. But, you know, the fascinating thing is, when Mahesh invites me back here in 30 years or so, I bet it'll be 8 seconds of no, it can't be 8 seconds. Yeah, it could be. 8 seconds of calculations will be 10 seconds actually. That computing will speed up as it has already enormously. So here are the experiments and simulations, and that's what's nice on this. Here's the experiments, and here, why is this not? It's interesting. Here I can see it says that the viscosity, no, the velocity, yeah, the viscosity, this should be centimeters per second squared, 0.22. The particles have a diameter of 0.5 centimeters. The density is 0.9 grams per cc. The porosity is 0.58. And T naught is 6 centimeters. I don't know what that means. But here we've lifted it up, and you see this is 5 centimeters in length. So this is something like 10 centimeters. And this is what happens as far as the experiment is concerned, and this is what happens as far as the simulations are concerned. Same starting situation, of course, and then it looks pretty similar, as you see here. Not lit as well as the experiment. These are now the results. We're looking at the thickness as a function of time, and here shows that the simulation and the experiments really work quite well. This is the position of the front as the initial position, and here's our simulation, and here's the experiment. Not bad agreement. Now, I like this slide, one of the best, because we could do theoretically both floating particles, i.e. those that were less dense and went over the surface, and settling particles, in other words, those that were more dense. And here are 4 shots of our calculations of floating particles. And here are 4 shots at different times, increasing time as we go down, of the settling particles. And what I like in some sense the best is how similar this and this look, except one is just inverted, because this is for falling sediments and this is for ones going up on the surface. Now, on the one hand, you should be shocked because the bottom is really very different to the top. This is a no stress condition. This is a zero velocity condition. But that doesn't seem to play much of a role, and they're the same. What I'll also say, and I'm just in the middle of doing this, so I can't say a lot, is if this was not a flat surface, but a bumpy surface, then it would be different again. And I've done some work on that. And if I'm invited again, I can talk to you about that. Only one of you need listen to that. Here we see it again. It's just a nice photograph of the same thing. And the color shows you what the velocity is. It's at the front, it's really going fast. And at the back, it's not going at all. But it's making a swirl in the fluid that looks like this. And here again, this is says that at the beginning, either for the floating case or the settling case, come off it. For the floating case or the settling case, at the beginning it's disturbed. It makes a difference, and there's no doubt that part of that may be, in a sense, releasing the gate, which you do in both cases. But in both cases, we, in a sense, open the gate or release the gate upwards. But there's a very good collapse at the end, as you see here. This is the non-dimensional front position as a function of time, and there's a good collapse both for the settling and the floating, which is interesting. Now, all this talks about the energy. I think we can leave that. We've also calculated the energy and how it dissipates as the kinetic energy goes down. I'd like to, we also plotted the Stokes number, and the Stokes number is the ratio of inertia to viscous effects. I was coming back to the question I was asked before. This is a photograph of George Gabriel Stokes, who was a very famous guy. He was a Lucasian professor in Cambridge for something like 60 years, as I recall. 55 years, incredible. This is the professorship that Stephen Hawking held, so it's really quite a famous professorship. He was the Member of Parliament for Cambridge University. It was remarkable until about 1950 or so. If you were at Cambridge University and lived in Cambridge, then you voted for your Cambridge MP, and you also voted for your university MP. So you had two representatives, and possibly the most famous MP for Cambridge University was Newton. That bright guy. For 5 years, he'd go down routinely to London and go into Parliament House. That bright guy only once spoke in his 5 years as MP. He got up once, it's recorded, and said, "Mr. Speaker, it's really quite stuffy in here. Could we open the windows?" That was all he said. And this is the new memorial to, I'm trying to get this to go. A new memorial to Stokes, and I was pretty influential in getting this set up, because I went to have a look at his gravestone, and it was really dilapidated, and so I don't want to go through. It took a lot of time to convince Pembroke, of which he was the master, to buy this or to get this new stone made. And what I found also fascinating in the argument is I wanted the Navier-Stokes equation to be written here, but Pembroke said, no, scientist is all you can have. And so it just says scientist. Anyhow, this just shows you how the Stokes number changes as a function of time, and how we can bring it together. I think that. Now, there are also interesting situations where particles come up and are lighter, and some of you may know about the Deep Horizon spill in the Gulf of Mexico, where BP had a pipe that basically had a crack in it, and it spilled all the oil, and there were particles in it, and they went up like this. And BP was enormously worried, because they thought that America would sue them. And nowadays they would have, but in those days it wasn't Trump. And they were really very nervous. And about a week after the spill, quite senior guy in BP came to Cambridge for a seminar, and we talked a little bit about that. And I said, look, I don't know why you're so worried. And he said, oh, it could come to the bomb. And I said, no, what is going to happen? It's going to be a plume, and it's going to spread, and it's going to be diluted by taking in the water. And then the particles, they're heavy, they're going to fall out and go on. And he went white, and I couldn't quite understand why. And he said, that's a total secret. How do you know that? And I said, I'm just using elementary fluid mechanics, which we teach undergraduates. And he said, we hired a scientific firm especially, and that's what they told us, but it was a secret. I said, well, what can I do? But that is definitely an interesting situation. I'd like to do more. Well, if I have some take-home messages, either light or heavy, small granular particles occur often in nature, and it's worthwhile finding out about them. I'm being a bit optimistic here. I will be able to say this better in a few years' time. Their paths can be numerically and experimentally well determined. And then I couldn't resist this. Watch out for the next volcanic eruption, both geographically and politically. And you all know what politically is talking about. Now, I've done a lot of work on this, as you see, but thank you for listening. And any further questions? Thank you, Mahesh.
So, can this, when water, you have those beads inside the water, initially it's sort of a pile, which slowly, gradually spreads out in the water. Can it be thought
in a reverse form when you have a pile of sand from which it gradually descends, because here buoyancy is affecting similarly what gravity would have affected if it had been reversed.
Yeah, well, it's the density difference that's the all important thing. If the particles are less dense than the fluid in which they are, they'll rise. If they're more dense, then they'll go down.
True. So similarly, if this situation, if thought in an analogous form to a pile of sand, where like the avalanche that happens,
Yeah.
at certain point of time, even a small grain of sand could start an avalanche.
If you're talking about a heap of sand,
Yeah.
it's less than the inclination angle, angle of repose.
Yeah.
And then it just goes to slide. Is it similar to that? Is the question.
Yeah, yeah. I don't think the details of the start make much of a difference. The total amount of sand or particles initially makes a difference, but that we started because it's experimentally so easy behind a locked gate, I don't think that makes much difference. What would make a difference is the number of particles there. And Mahesh has given a good example of saying if you have grains at the angle of repose, they'll come down pretty much similarly to if you have them in a cylinder.
So there are several literatures that talk about this specific example when you have a pile of sand at an angle of repose, and you just add one grain to that, and you have several avalanches, small avalanches that come on that pile of sand, and they come in sort of chaotic form rather than being deterministic.
Yeah, but I don't think, well, I don't know, where you can add just one grain of sand and that will send the whole thing going.
Just like an avalanche, even a small sound can start the avalanche.
I don't think that's so. You need quite a lot of sand to start the avalanche. It's not a little, you need quite a bit of energy to get it going if it's been sitting there for quite some time. That's all. Oh.
You spoke about underwater volcanic eruptions. I was thinking, the first example that you showed, the experiments that you showed, was the liquid water?
Yeah.
And I presume there was air on top.
Yeah.
So these particles that you are releasing are less dense than water, but heavier than air.
Of course, yeah.
So the air-water interface acts as a confining because it's not going to shoot out into the air.
Correct.
In the oceanic case, when you have an underwater explosion, what is observed? Do you get a plume which much before it hits the air-water interface, it already spreads out like a mushroom, or does it go all the way and then start spreading?
There are some of each sort. There are volcanic eruptions on the base of the oceans all over the world, more or less, well, all over the oceanic world. And some are rather weak and the particles don't get to the surface, and some are stronger, more output, and the particles get to the surface, and then with the hot air and muck with them, they go into the atmosphere. So both are possible.
Of the explosion which decides.
Yeah, it depends. Yeah.
So there is no role of the surface tension of the liquid.
Well, the surface tension in the experiments may play a bit of a role at the end. We've not varied the surface tension at all, and we haven't put that into our calculations. I don't think it plays a large role, but surely it could. And I mean, it's a good question. And what I immediately think of is if you pour honey onto a flat surface, it'll spread, and surface tension doesn't play a role at all. It spreads at a rate that's independent of surface tension. But at least, again, I don't know what it's like in India, but in Australia, when I was a little boy, you used to measure temperatures by putting a thermometer in your mouth that had mercury in the bulb, and the mercury expanded according to the temperature. Well, we little kids used to break it. Oh, accidentally, Mum, I don't know how it happened. And then you'd have a very small blob of mercury, which you could play with. And their surface tension plays a large role. It would sort of stay as a blob and it wouldn't spread. So surface tension definitely plays a role in some situations, but generally pretty small.
So did you have, I saw the simulations, did you have an analytical model to predict the front?
Oh yeah, well, we're just solving the Navier-Stokes equations by DEM. Yeah.
No, but analytical, like the way that you had for your gravity flow, where you just had a balance.
Well, yeah, you're here because there's quite a lot going on. It's not a simple solution that you can analytically write down, but yeah, you need to solve the equations. That's what the DEM technique is about.
Can you go back to your slide on, yeah, this one. There is a major error in this particular slide.
There's a
You might
major.
get into trouble.
No, we can write a paper about it.
Yeah, there's a major error.
What's the error?
Look at the title.
Look at the plane.
Yeah, you get into trouble if you're in the US now.
I haven't yet. What's wrong with the plane?
It is now called the Gulf of America. You didn't know that?
The whole world is going to change due to that damn man. And soon he'll own Canada as the next state and Greenland and make the Gaza Strip a wonderful holiday resort. Yeah, well, thank you for pointing out my error. I'll make it better next time. Well, I'd just like to say thank you very much for hosting me. I've really enjoyed it here. I've had a great time, except much of this lake has gone away. And when I was here the first time I was here, I suggested I might go for a swim. And people laughed. But I was told a few days ago there are as many crocodiles in this as there were then. But the area is getting less and less. So they're seen around in the campus.
There was one a few days ago loitering around.
What, did somebody take him to lectures and
We made him an engineer.
teach some mathematics to him? 1, 2, 3. Okay.
So let us thank Professor Huppert for such an insightful talk.
Thank you very much.
I would like to call Professor Mahesh to deliver the vote of thanks and also hand over a memento from us.
Thank you very much, Mr. Huppert. Wonderful talk.
Thank you very much.
Insightful. And always, I've seen you when you give presentations, always a new paper that you write. So it's very, very inspiring for many of us on this. Okay, and so with that, I think there's a small memento.
Oh.
Doesn't look very small.
Small memento.
Let me just, there you go. Right. Just be careful when you come down. There you go. I have no idea what this has.
It's so heavy.
Sir, 1 second, sir. I'll hold the tray.
Yeah, you hold it.
No. You may take this and give it to her.
Okay. Right. Okay.
But I wanted the tray.
So that's what this is. Yeah. Yeah.
Well, thank you very much.
Thank you. There you go.
Now, actually, could I have a few more minutes?
Sure.
I don't know if I did this last time.
Yeah. This is not for me.
Can I give you all a problem to solve? Did I do this last time?
Yes, I think you did.
Oh, I'm sorry. Well, those of you who were here will remember.
But I'm sure there are others who have not. So they can take it.
Those who were not here at the last time, do you want to vote? 1, 2, 3, 4, 5, 6, 7. Which is going to be filled first? Those who vote for 1? Who's going to vote for 1? No one's going to vote for 1? 1 vote for 1. Where's, I have some paper.
7 has a hole at the bottom. Is that what it is?
I'm not saying anything. I'm just putting this up. 1 person had voted for 1. 2, 3. I can't count that far. 1, 2, 3, 8, 9, 10, 13, about 15. I can't count that far. You may know, just as an aside, there was a very capable mathematician who was in a train going to the airport with his wife, and he was clearly worried. They had all the suitcases, and she said, don't worry, dear, we've got all the suitcases. He said, no, they're not all here, we've lost one. Dear, we have 8 suitcases, and there are 8 suitcases here. And he said, no, look, 0, 1, 2, 3. Okay, 15 at 3 that was, yeah. 4, 1, 5, 1, 6, 1, 7, none. Now, Mahesh, if I did this last time, what's the answer?
No, I think this problem has changed since the last time. I don't know. I don't remember what it was. It looks like 3.
Well, you know what the answer is? You're all wrong. Every one of you. First of all, for a lot of reasons. First of all, what I see here is 1 drop. Whoops, come on. Oh, what's happened now?
There's only 1 drop.
There's only, oh. There's only 1 drop. Say we imagine that this is a flow. Is this a flow of a very viscous fluid? A not at all viscous fluid? Is it going rapidly out of this tap? Is it going slowly out of this tap? So that's why you're all wrong, because it really depends on things like that. And in addition, I bet you all thought these were cylindrical cups. I never said that. Maybe number 1 has a great bit that slopes down here, and all the fluid goes out of 1. You know, you can imagine the geometry can be really quite different. And I think this is a wonderful example of the fact that, as is partly indicative of the questions that were asked me, you have to know exactly what the question is and what's going on in order to get the correct answer. But when 1 drop falls into an array, it's not very interesting. The real problem is, if I may say, maths is so very difficult. And, you know, I know this is a chemical engineering department, but I find maths so very difficult. For example, 10 plus 10 equals 20. You all know that. But 11 plus 11 equals 22. So how do you work out what to do? That's enough.